Okay, for today, what we'd like to do is revisit the launching of a projectile from a cliff and see if we can find a way to maximize the area that's underneath this trajectory. Now, we previously have done a problem like this where we worked out the range, meaning where it lands as a function of theta. Here's the result. It's not super clean, but this first bit is exactly what we would get if we had h equals 0. So that's the usual range formula on level ground. This extra little square root piece is what we get by including this factor of the height. It was convenient to define some dimensionless parameter, I'll call it beta, which is 2gh over v naught squared. It's something like a ratio of initial gravitational potential energy to the initial kinetic energy. But notice it has no dimensions and it scales like h. So when h equals 0, that's the same thing as saying beta equals 0. We picked up this extra piece. It's got a cosecant squared in it. We could rewrite that in terms of a sign, and maybe we will in a sec. But we want to now maximize this area. Let's say the area under here is A. Okay. So finding the area underneath this would require our trajectory equation, which we've also written down many times before. So let's start with that. It'll be an integral from 0 to r of the trajectory. Okay, so that is our area integral. Now we could actually just do this integral. It's not that hard. It's a polynomial in x. We could plug in the r and then we could try to maximize. But I'm going to take a little bit of a shortcut because I'm interested in maximizing this area. So right off the bat, I'm more interested in setting dA d theta equal to 0. That's really what I want to do here to maximize the area as a function of theta, launch angle. I want to know what launch angle maximizes this. Well, what I could do then is I can think of this as a fundamental theorem of calculus type derivative. I'm taking a derivative of an integral. So the Leibniz rule should basically give me how to do that derivative. So first off, notice that I need to take my expression y, plug in r, and maybe we should also note that y is a function of theta. I'll make that explicit up here. So is r, by the way. And then we have to realize that what we first do is take the expression itself, get rid of the integral. I mean, that's what a derivative kind of does, is you undo the integral. So that'll just be y. But I evaluate it at r, at some theta. And I multiply from the chain rule by dr d theta, the derivative of what I'm plugging into my integral, or into my function. Technically, I should also plug in 0 and subtract that off, but the derivative of 0 with respect to theta is 0. Then, however, I need to worry about the fact that there is a dependence on my integrand of theta. So I'm going to add to this the integral of dy d theta dx. Okay, so this derivative is going to hit two different pieces. It hits the bound during the fundamental theorem of calculus application, and because the integrand itself depends on theta, I have this second piece where it comes inside as a partial. Now the beauty about this is this first term is 0, because y at the range is 0. That's what I'm defining the range via. We're just saying that's where it hits the ground. So that term is 0. That's convenient. So now I just have to do this derivative with respect to theta of what's inside. I still have my integral. This is a constant, so that goes away. Derivative of tangent is secant squared. Remember, we're keeping x constant at this time. And then the derivative of secant squared can come from the chain rule. So the 2's will cancel. We could also rewrite it in terms of a tangent if we wanted. I'll get a single secant, and then the derivative of secant is secant tangent. Okay, now I can actually do the integral, like I could have done here, but notice that now there's one fewer term, so maybe it'll be a little easier to set this to 0. I'll kind of do these in one step together. The antiderivative here would be a 1/2 x squared, and then I'll plug in r. The lower bound will be 0 for all of this. This next term will be a 1/3 x cubed, but I'll just plug in r. All right, so we have our expression. I want to set the whole thing to 0. Let's see if we can just factor out as much as we can. I can pull out an r squared from both terms. I can pull out a secant squared from both terms. And now what we want to do is set this to 0. R is not 0, hopefully, if we're trying to maximize this. Secant is not going to be 0 ever. And then we just have to set this equal to 0. Unfortunately, this is also where the r itself comes in. Don't forget that also depends on theta. So using this expression for r, let's at the top of the next board just write this out, having already pulled things apart and substituted in our expression for r to finish the algebra. Okay, so here's what we get. I went ahead and there was a 1/2 equals something or minus something with a 1/3. I went ahead and just sort of pulled out that 1/2, moved it over to the other side as a 1. This was all the stuff multiplying r with the extra 2 up for the 1/2. And then this is r itself. And let's try to clean this up a little bit. We want to solve this for theta. So we can partially simplify this by just canceling out these v0 squareds and these g's. That's good because, well, none of that should really be relevant. The only place we have a dependence on the height that we started with is in this beta. We can also simplify here. Tangent and cosine will give us a sine. So I'll write this as a sine squared now. And then let's pull this cosecant squared out of the root by finding a common denominator in there. So all of this will become, let's see, I have a sine squared under here, so I'll have a beta plus sine squared theta under the root. All of that is over the square root of sine squared, but that'll just be sine. And then there's this plus 1 out front. I guess I'll make that into a sine over sine as well. And that's kind of nice because then this sine and one of those sines also cancel down. So let's write a little bit of a cleaner version. And actually, while we're thinking about it, let's do one last thing, which is I'm going to make a little substitution over here. Let's just let u equal sine theta. So look cleaner with that. So we have 1 equals 2/3. I still have 1 sine theta here, so that's u. And then inside of the parentheses, I'll have a u plus root beta plus u squared. And again, I'm trying to solve for u here. Now, this looks pretty ugly. Turns out it's not going to be as bad as we think. So let's expand. We'll square both sides once I get the root alone and see where it goes. Okay, so let's go ahead and I'll move the 3/2 over. We'll have a u squared, and we'll have a u root u squared plus beta. Let's subtract. I'll square both sides. This looks like it's going to be a quartic, but it'll be better than we think. Don't worry. This side will end up having a u squared plus beta on it as well. This side, when we expand things out, will be u to the 4th minus 2 times the cross term will be 3u squared and then plus 9/4. And now we can see that when you expand this out, oh yeah, the u to the 4th here and the u to the 4th here will cancel. That's kind of nice. I'll be left actually not even with a quadratic formula. It'll be quadratic, but I don't have to use the quadratic formula. There's no linear terms in u. So what do we have? I'll leave the 9/4 over here. On this side, I'll have a beta times u squared and then a plus 3 times u squared. So beta plus 3 u squared, which at the end of the day gives us the result we're looking for. I'll squeeze it in over here, that u, dividing and taking the square root, is going to be 3 over 2 root beta plus 3. Remembering that u is sine theta, we now have our optimal launch angle. So sine theta, maybe I'll call it theta star. This is the angle that maximizes the area, is 3 over 2 root 3 plus beta. So it does depend on beta, obviously. We should note that it'll change depending on what the height is. We should also check that we recover our previous result, that if this is launched on level ground, the maximal area was a 60-degree launch angle. Let's see if that's true. In that case, beta equals 0. Okay, beta equals 0. 3 over square root of 3 is square root of 3, and root 3 over 2 does have an arc sine of 60 degrees, so that checks. That's nice. It also means that as beta gets larger, notice that my launch angle of maximal area gets a little smaller. Beta is downstairs. And that kind of makes sense. You want to head out a little bit to gain more area. If you're already starting up a little high, you don't have to spend as much going up as you do going over. The last thing we might want to do is actually plug this back into our area and find out what is that maximal area in terms of beta using this. So to do that, let's go ahead and rewrite our integral for the area. We'll quickly do it, and then we will figure out what that maximal area is. Okay, so to make this integral easier, let's first find the range corresponding to this angle by plugging it into our range formula. Maybe I'll call that R star. So I have a V naught squared over G. I'm going to rewrite that in terms of beta and H just to make things look a little cleaner here. So notice that 1 over beta will have a G and a V naught squared. There'll be a 2 there as well that I'll have to add in. So let's see, 1 over beta. I'll need to put an H on there, of course, to give me the right units. And then we just got to figure out where the 2 goes. So I added a 2 in the denominator. I need to put a 2 in the numerator. Sine theta, we already know. It's this value right here. Cosine theta is going to be a little more annoying. It does come from the Pythagorean theorem, so let's calculate that real quick. Cosine is going to be square root of 1 minus sine. So this will be minus 9 over 4, 3 plus beta. Finding the common denominator there, oh, that's a square. No, that's not a square. Finding the common denominator there will give me a 4 times 3 plus beta. 4 times 3 is 12. 12 minus 9 will give me a 3. So I'll have root 3, and then I'll still be left with this 4 beta. So plus 4 beta all over 4 times 3 plus beta. So that'll be my cosine. Let's plug that in as well. There'll be some nice cleanups that come here. And actually, while we're at it, let's just pull the 2 out of there. Okay, there's my cosine. Thankfully, that's the only place a cosine shows up. And then there's the piece in the parentheses. So we have a 1, we've got a root, we've got another 1, and then beta times the reciprocal of this squared. So beta, when I reciprocate and square, I'll end up with a 4, a 3 plus beta, and I'll end up with a 9 in the denominator. Did that fit? It just barely fit. Okay, great. We can clean this up. 2 and 2 cancel. We have an h over beta. This root 3 plus beta and this root 3 plus beta are still there. And I might as well put the 3 and the 2 that are left over here. So we have a 3 plus beta. There's still this square root, but let's simplify this first. So again, common denominator, I'll have a 9 plus beta times 4 times 3 plus beta all over 9. And in this particular case, not much we can do about the combination here since I'd end up with a quadratic in beta. But let's do it anyway. So we'll have a 9, we'll have a 12 beta, and a 4 beta squared. And then we've got an over 9. Now let's see, can we factor that at all? 2 beta plus 3. Yeah, it's a perfect square. Oh, that's convenient. Okay, I'm kind of following this down off to the side here. This whole thing is actually 2 beta plus 3 over 3 quantity squared. How convenient is that? The square root kills the square. I then need to add that to 1. All right, we're almost done here. 3 plus 4 beta under the root is still there. And then I have a 1 plus 2 beta plus 3 over 3. Finally, bringing all of it together, a 3 up here. The 3's will cancel with this 3 that's out front. This becomes 2 beta plus 6, but that can be partially canceled with the 2 here, giving me a beta plus 3, and then a 3 plus beta, canceling it all the way down. And so at the end of the day, we get the very nice result. Might not have expected it from the amount of effort it was taking, for our range corresponding to maximal area. All right, let me save this off to the side, and now we'll go finish things off by plugging these into our area. Okay, we're ready to finish it off. Here's our trajectory equation once again. We're finding that maximal area corresponding to this launch angle. The r is going to be the r star we just found. The only thing left to do is do the integral and then write down what tangent and secant squared are, again, in terms of these. Maybe I'll put them as optimal angles. So polynomial, pretty easy. I'll go ahead and do this real quick. So the 0 part will not contribute. I'll have a 1/2 r star squared. While we're at it, tan theta star is sine star over cosine theta star. The 1/2s will cancel. The root 3 plus betas in the denominator will cancel. And I'll just be left with 3 over root 3 plus 4 beta. I can see that's going to play nicely with the r star. And then the last term will have a 1/3. So I'll have a g r star cubed over 3. The 3 will combine here to give me a 6 v naught squared. And then secant squared is just going to be this thing flipped and squared. So I'll have a 4 from the 2 squared, and then I'll have a 3 plus beta over 3 plus 4 beta. Okay, so that's our expression. We just have to finish evaluating it with this r star. Okay, so substituting in, what do we got? I guess I'll do term by term. So we have h squared over beta. We've got a root 3 plus 4 beta. Not much we can do there. We're going to hope that all of the terms kind of look like this. The next piece, well, the 3/2 I can pull to the front. R star squared will have an h over beta squared. And then this thing will partially cancel with this root and just leave a single root 3 plus 4 beta. Okay, that's looking kind of good. And then finally over here, what can we do? Well, this will partially cancel down to a 2. G over v naught squared, actually let's do one better. 2g over v naught squared is almost beta. So let's make that whole thing into h over beta. I'll keep the 3 here, don't forget that. The r star cubed will have another h over beta cubed. We have a 3 plus 4 beta, which is raised to the 3/2 power. It's canceled down to a 1/2 power by this. And then there's a leftover 3 plus beta. hanging off the end from that secant squared. Okay, let's factor whatever we can out of this. Obviously, it's an area, so there should be a distance squared, which there is. There's an h squared in all of these terms. Whoops, let's see. Yeah, I messed up here. This should have been beta over h. And actually, the 2 is probably in the wrong spot. No, the 2 is in the right spot. Okay, so anyway, the h's here will partially cancel down to an h squared. Notice there's also a beta in each one of these terms. I'll actually go ahead and factor out a beta squared from each term because this beta over beta cubed also gives me that. So I have h squared over beta squared. There's also this root in all of these, 3 plus 4 beta. So now let's see what we get when we factor that out. So I left a beta here. Most of this cancels. I just have a 3/2. It's not so bad. Over here, we have a subtraction. I have a 1/3. And then the h's and betas have already been factored out. The root's already been factored out. And I have a 3 plus beta. All right, we're almost done. 1/3 of 3 is -1 here. I'll have a minus beta and a plus beta. Well, that's convenient. Those cancel out. Sorry, a -1/3 beta and a plus beta. So that'll give me a 2/3 beta. And then 3/2 minus 1 is going to be 1/2. And then finally, let's rewrite this just slightly by finding a common denominator of 6. So I can rewrite these two fractions. Here I'll have 3/6. Sorry, not 3/6, 4/6. And over here I'll have 3/6. And notice that what I'm left with is 4 beta plus 3, which is exactly what's under my root here. It's just all over 6. So my final answer here is going to be h squared over 6 beta squared. And then 3 plus 4 beta, I got a root of that here and then a first power here. So this will be to the 3/2 power. That is my maximal area under this projectile launched from a cliff, depending on beta. We might worry a little bit about what happens when h equals 0, because I do have this denominator of 0. But I will leave it as a homework exercise to check that, in fact, this is well defined as beta goes to 0, because actually h and beta are proportional to each other. So those will cancel out, and I'll just be left with what we'd seen previously. All right, so there it is. Both the angle that launches with maximal area and also the area under the curve itself. QED.